Welcome to the second appointment of the Institute of Advanced Studies organized by AI4I, the Italian Institute of Research on Artificial Intelligence for Industry, and jointly with Fondazione Compagnia di San Paolo. Let me just quickly introduce the Institute. We have been here for almost a year now. We are active in many directions, particularly building a large applied research center on artificial intelligence with particular focus on industrial applications. But we are also active in many other respects, all around the idea of helping the national and the European industrial economy to thrive, to gain further competitiveness and efficiency in the worldwide arena, thanks to the development and the adoption of new technologies. This is the general purpose and the general mission of our institute. The Institute of Advanced Studies is a joint venture, as I said, with Compagnia di San Paolo, with a particular focus, which is to invite and expose to our broader ecosystem the best researchers and experts in AI worldwide, so that we can have, we can be fed by all this knowledge. As you can see, I'm trying to speak low because this is an open environment and the people are working, so I'll try not to be too loud. So thank you for your understanding for this. And I see that you're wearing your devices, and I hope this will help you. So thank you very much. Now, let's come to this second appointment. It is an honor and a pleasure for me to welcome Professor Albero Bemporad. Albero Bemporad is a long story in AI research and academia. He studied in Florence, and then in the Washington University, in ETH in Zurich, and then Siena and Trento. And finally, he landed at the EMT School for Advanced Studies in Lucca, where he's professor of control. He's also founder of a company, Odis. The company is active in applying advanced control methods to industry, so exactly spot on, and particularly in the automotive sector, but not only, of course. So it thus combines academic excellence with entrepreneurship and technology transfer. Today we'll talk to us about AI methods applied to the frontier of control systems. So please join me in a warm welcome to Professor Bemporad. Thank you.
Thanks, Antonio, for the introduction. It's a real pleasure to be here today in and in order to be at the Institute for Advanced Studies, I thank the Compagnia di San Paolo Foundation and the AI for Industry Foundation for inviting me. In particular, I thank Antonio Calegani, the director of AI4I, and Fabio Pamolli, the president of AI4I, for this invitation. So today I will talk about many research activities which are at the frontier between control, research and control systems and research in AI, I would say general machine learning methods applied for and developed for solving technical problems that arise in control engineering. Most of the results are recent results that I have obtained together with my research team in Lucca and other co-workers. And many of these activities are actually under the umbrella of the ERC project Compact for computational model predictive and adaptive control tools, which is funded by European Commission and funds this research for 5 years, starting from last year. So let me start about the general picture about control systems, or say industrial automation in general. The method that I will talk about today are I often call a hidden technology. Control is often called a hidden technology because it's not related to a particular industrial sector like automotive or aerospace or manufacturing, but actually it's a technology that is horizontal with respect to many, many applications. And I'm listing here many of these application areas where you find control systems and automation applied and quite relevant, from automotive, aeronautics, aerospace, manufacturing, chemical, process control. So many different industries that require advanced control methodologies to work. And it's not only manufacturing, traditional industry, but also other type of sector where you would not expect, like logistics or the management of environmental systems, down to medical devices. So many, many different applications. And all of these application areas have in common the need for, in the end, a piece of software which takes decisions in real time, reacting to measurements coming from the physical system to act on the system, so to make the system behave the way we want. This is actually quite a large market. I found some data here. Worldwide, last year, the figure was around 2 billion US dollars worldwide, and in Italy, 5 billion, so it's not a negligible market. And what is most interesting, I believe, is that this is expected to grow quite considerably in the next few years. Now, when it comes to designing those control systems, there are several methodologies you can use. I'm listing here probably still the most used methodology, which is proportional integral derivative control. This is the traditional way of designing control system that dates back to decades, many, many decades ago. And these are n-grams. I don't know if you are familiar. This is the frequency the words appear in books according to Google. You can see starting from the 70s, it's not working. Starting from the 70s, the growth of the important PID control. Nonlinear control is another advanced control methodology. Has some hip in the 90s, now still applied. System identification, it's another technique that became popular in the 90s. It's still popular. It actually is getting more and more popular because it's a data-driven design approach. Now, when it comes to model predictive control, you see how it increased attention starting from the 80s in the process industries. It's getting more and more popular, especially in latest years. Of course, not comparable with machine learning, where you see a kind of exponential or double exponential, I'm not sure, but quite a growth that we all have witnessed in the recent years. And what I actually perceive and I see in many R&D centers in industry dealing with control system design is to focus on both MPC and machine learning and how to combine those powerful technologies together to get the most benefits. So what I will talk about today are some methods that are in this intersection of model predictive control and AI methods. So just in a few words, what is model predictive control and why it's called model predictive control? This is a general picture of a control systems. I guess many of you are familiar with. You have a process you want to control. Let's say you're a vehicle. You want to have a driving assistance system that generates the commands on the vehicle. For example, the torque produced by the engine, or the steering, power steering, to steer the vehicle in real time based on measurements, for example, of camera or other sensors, in order to let the vehicle do something, in particular to track certain reference. For example, you want to keep a certain velocity or keep certain lateral distance on the road. And every control system works like this, so a feedback loop where an algorithm decides the commands to actuate the vehicle in real time based on measurements. So the control system differs based on the type of algorithm that you have in the piece of software that runs in this case on the vehicle. Now, what is particular about MPC is that the control system exploits explicitly a dynamical model of the process that you are controlling to make predictions of what the process will do in the future if you apply a certain sequence of maneuvers. And among all those possible predictions, selects the one that is best according to a certain performance index. And it does this repeatedly over time. So at each time, replans, acts, replans, and acts. It is quite a natural, if you think about it, it's quite a natural approach, the same approach that you use when you drive. When you drive, you look ahead a certain amount of time or space. So say some meters or tens of meters in front of you and decide what to do. So based on what you see, so based on the measurements you get, you decide I want to now say slow down and then steer and keep replanning as you go along the way. So MPC has a similar idea. Now to state this more, say, mathematical form, you have a prediction model, which is a model describing the evolution of the outputs that you want to control over the set point, over time. K here is the time index. And this is the model. So think about the difference equation that describe the way that the output evolves over time based on the inputs. You have a performance index. For example, you want to minimize the error between the predicted output and the reference you want to achieve. And also penalties on the actuation. And also very important in application is the ability to specify that there are constraints. So you're not free to actuate the system the way you like, but there are some bounds, upper, lower bounds, or some other type of constraints that you have to satisfy, both of the inputs and in general the outputs. So at each sampling instant, the algorithm will compute this prediction, minimize the performance index, so solve an optimization problem which selects the best sequence of inputs over a certain prediction horizon of n steps. Then out of this selection of the sequence, it will only implement the current move, so the input for the current time instant t, because at the next time step, it will acquire a new state, a new measurements, a new state estimation, and then replan a new sequence and so on, and do this repeatedly over time. So this is the core idea of MPC as a control algorithm. So what you need is a performance index to minimize and a prediction model and the constraint specification that you have in your application. Now, is this a new idea? No, this is actually now a pretty old idea. Actually, the first papers are in the 60s from people in the process control industry, and also there is a Russian paper from '63 which is proposing the use of linear programming to solve digital control problems. Now, the big, say, technological jump happening in the 80s when in the process industries, people had the need to have online optimization, which could run on the computer due to the slow sampling time to solve complex problems with many inputs and many outputs where you really want to optimize a certain quality of your products. Now we see that it's spreading in other industries, and in particular in the automotive industry, where the same ideas are applied to now much smaller, maybe simpler processes, but which run at very high frequency, and also on small hardware. And indeed, with our company, Odis, Antonio was mentioning, we are still collaborating a lot with General Motors in the US to design MPC control systems that actually went to production now a few years ago in 2018 for engine control and also for torque control in a high volume production. So we have General Motors designing the say, the concept of the MPC and also provide the software to implement these on standard automotive hardware, so that it was possible to put these in production. And this production, actually, there are many more that are in production these days. I cannot mention here. So this is kind of a success story because it was actually the first, at least non-documented time where such methodologies were applied and placed in production in high volumes by General Motors. Now, what I will talk about today, that's the focus of my presentation, is on, say, 3 ingredients. How to get the model from data, and in particular, how to get good, simple, but effective nonlinear prediction models to explain the input-output relation of the variables in the system you are controlling, and also how to adapt the model in real time by learning disturbance models, and also how to possibly simplify the online optimization. And I will show a special type of learning algorithms that we have developed to achieve these goals. So let me start with the modeling, and in particular, to learn control-oriented models of dynamical systems. And I like to mention this saying by the famous statistician George Box: all models are wrong, so don't expect to model the system perfectly, but some are useful. So we have to model the system in a way that it's useful for what we want to do. In particular, it's useful to optimize over the model in real time. Why do we want to have simple models? Because there is a one-to-one dependence, or say direct dependence, between the complexity on the model and the complexity of the controller. Since the model is used to set up an optimization problem in MPC, the more complex the model, the more complex is the optimization. So you really want to try and simplify the model as much as you can, so that you can simplify the optimization. So as a result, we look usually for small-scale models. Small scale means, say, up to 10 states, and say 4 or 5 inputs and outputs, with a limited number of coefficients, because the more coefficients you have, the more complex is the model, also to implement in small hardware. So we talk about models, say, with 1,000 coefficients, so nothing compared to the 300 billion parameters you have in large language models. So it's a different type of model we look for. Also, we want to limit the nonlinearities. The more nonlinear is the model, the more difficult it is to optimize. So we try to get as linear as possible without sacrificing the representability of the model of the real system. So we tend to avoid very deep neural network, rather keep few layers only, so that the model remains not excessively nonlinear. And usually, you're faced with this problem of getting the best model you can out of a poor model class. So since you have limited the complexity of the model, and you may have quite a rich data set, so you can acquire a lot of measurements from different sensors, maybe even with some redundancy. So usually, overfit is not the main issue. Sometimes it is, but it's not usually the main issue if you have tons of data. Is that you're looking for a simple model, so you want to really get the best among these limited class of models that you have selected, the best model representing the process that you are controlling. And then you often have computation constraints, so you cannot afford a supercomputer for doing the training, like the one that we have around here, but rather you want to use the training on a standard computer like a laptop. Of course, sometimes you want to parallelize, so solve in parallel, say 1,000 times the learning problem to try to get the best model. But you want to have, say, training algorithms that are not too complicated to implement. So that means that for say, learning such control-oriented model requires quite a different machinery from the machinery, the advanced machinery that you need instead to learn large models like large language models, for example. So we don't deal with images, with vision, with videos. So just expressing relations among quantities that evolve over time. And in particular, neural networks are a powerful framework. You can also, here I have a general form for the model. So f, x, f, y are general nonlinear parametric functions that explain the evolution of the state of the model and the output. This can be feed-forward neural networks, could be other type of networks, could be also physical system or gray box system, physics inspired. So it can be any parametric function. Your task is to determine the coefficients of the function that best fits with the data, as in all model learning problems. We are dealing with recurrent models, so the training problem can be phrased as given the data set, so given a collection of inputs and outputs, you want to find the model that best fits the output according to a loss, for example, mean square error, with some regularization. And this optimization is not only with respect to the parameters of the model, but also with respect to the hidden states. These are artificial variables that you introduce. They are not physical variables. Okay, so it's different from training standard nonlinear regression problem where you can each data point is independent. Here, all the data points are linked by the recurrence over time. So how to solve this problem? Well, you can take the optimization problem and eliminate the state variables just by replacing the state with the state update equation recursively. You will end up with a function which is quite nonlinear, but it's a function v, which depends only on the model parameters and the initial state. So the problem is to minimize this function with respect to the parameters and the initial state. So this is a nonlinear optimization problem. You can use different methods. The most popular are gradient-based methods. Thing is that this can be very complicated function, but with autodiff tools, you can compute this function and the gradient quite effectively. So you can use different gradient descent methods. For example, Adam just follow the gradients with some coefficients alpha t, which are determined based on an adaptive moment estimation, or you could use any other variant of Adam or just pure gradient descent. The issue with this method that only go in the direction of the gradient at each iteration is that they converge slowly. They can be very practical to implement because they're simple, but it can be very slowly, not only in theory, but also in practice. So I will show you some example. It can take quite many iterations to converge to a good model. Stochastic gradient descent methods are used a lot in machine learning for training large models. Here, they're not very appropriate because, first of all, you cannot separate easily each data point. So you could create mini batches by collecting independent experiments or by relaxing some of the state update equation, then use what is called multiple shooting ideas in optimal control. But these are not very effective according to what we have seen. Newton's method would be ideal. So if you take into account the Hessian of this loss that you want to minimize, you will have excellent second-order convergence, local least convergence. But these are more difficult to implement. In particular, you have to compute these Hessians that even if the model is simple, it can be very, very complicated because you have to auto-differentiate not really the full Hessian, but at least Hessian product terms are a lot more computationally heavier. Now, a good trade-off between pure gradient and second-order method are so-called quasi-Newton methods because they have very good convergence speed, so they provide good solution quality within a limited number of iterations, but they only require the gradient. So it's a good compromise. And in fact, that's what we have been focusing on in the last few years. So how to train recurrent models using quasi-Newton methods. In particular, now we'll show you how to use LBFGS and variants of LBFGS to to solve the training problem. So again, the problem, let me just rewrite the model in a slightly more general form where I have a linear part plus the nonlinear part. So you have a linear bypass on the output of this model for the state updated output equation. I want to minimize the loss between the measured outputs and the predictions that I make with the model, subject to the dynamics. Okay, so if I substitute and say call z the variables, so the initial state and the vector of parameters of the model, which in this case are all these matrices A, B, C, D I need to learn, and the parameters. Say these are neural networks, they will be the weights and bias terms of the neural networks I use here. I can rewrite the problem as the problem minimizing a smooth function plus a regularization term, which can be smooth, so differentiable, continuously differentiable, but can also be non-smooth. So if they are both smooth, this is a smooth nonlinear optimization problem. You can use, as I was mentioning, different methods. In particular, LBFGS, which is now, I would say, a dated method, but it's still probably the most efficient method. And you find still excellent implementations of this method interface with Python, MATLAB, Julia, whatever language. So this can be exploited to efficiently solve the training problem. And the gradient can be computed quite effectively by automatic differentiation. The problem is with the regularization. So remember, our aim is to have simple model. And sometimes simplicity means to try to, say, zero part of the model. For example, try to eliminate states that are redundant so then you have more compact models. Or sometimes you have redundant inputs. You don't know which inputs you really need. You can try to reduce automatically the input that you need to provide into the model using what are called group-Lasso penalties. So you penalize some groups of the coefficients, try to have them zero at the solution. Or you can just parsify, so with a penalty on the one norm of the variables you're optimizing. At the solution, you will have several zeros induced by the one norm. Or this could just be you over-parameterize a neural network and try to reduce the number of layers, for example, in neural networks in residual form. Now, how to use methods like LBFGS, which are good for a smooth problem when you have these non-smooth terms. Here is a simple, I would say, simple idea which I explored in this recent work, which is the following. So if you say X are your optimization variables, if you split the positive and negative part of these variables, and this is a standard trick you do, for example, linear programming, then you can show that the regularization can be written as the sum of the regularization over the positive and the regularization over the negative of the negative part of the variable. So that means that you can solve a smooth problem with bound constraints. And one particular example is when you have quadratic regularization, this becomes a quadratic, strictly convex quadratic term on both y and z. While if you just substitute y minus z, would not be positive definite, just semi-definite. And moreover, if the regularization, like the group-Lasso, has certain properties, in particular is convex, symmetric with respect to each component, and increasing for positive variables, then you can show that you can write the regularization as a regularization over the sum of the positive and negative part, so that this whole function here is smooth over the set of positive variables. It's actually differentiable over the set of positive variables. That means that these problems with the regularization, with non-smooth regularization, like L1 and group-Lasso penalties, can be still solved quite efficiently, as we show in a few examples with standard box constrained LBFGS methods. And in fact, I put together a package for doing this. It's called JAX SysID because it's based on JAX to specify the model and to auto-diff, in particular, the model and the cost function associated with the training problem. It's in Python, and it's quite simple to use. So you specify your state function as a function of the parameters you want to use, which are optimized, and you specify how many states, inputs and outputs you have. Then provide an initial guess just to specify the dimensions of these parameters. For example, this could be matrices or weights and of the linear system, the regularization you want to use, and then you run the fit on the training data and you will get a model out. And you're welcome to download and use if you're interested. This tool is for nonlinear models as well as for linear and also for static models as well. And here it's a particular class of model which is quite useful for control design. These are called quasi-linear parameter varying models. So you have a model which is linear. So the relation between the input U and state X and the next state and the current output are all linear, but they depend on a parameter P by a linear combination of given matrices. So it's a linear combination at each time given by this coefficient pk, where pk's are endogenous, so they are nonlinear functions of the state and input variable. So in the end, this is a nonlinear system, which looks like a linear parameter varying system, but is indeed a nonlinear system. But it's a quite powerful class, and you can do a lot of things with this class of system for control designs. And in JAX SysID, I have a specific method for the identification of such models. You specify how many states, input and outputs, and parameters P you have, and what is the function here you want to use to generate the P's and their initial parameters. And here is an example. So generated some data from this toy nonlinear system with some noise on the data. You want to identify an LPV system, quasi-LPV system, where the P is a simple two-layer feed-forward neural network with 6 neurons. And so it's quite a simple one. But these are the results that you get with a purely linear model. So the fit, this is the best fit rate, so how well you fit the input-output data on a test data set. 100 is the best, 71 can be acceptable, it's not too high. If you have just one parameter, you're already up to 93%. And if you increase the number of parameters, then you increase the expressiveness of the model, the quasi-LPV model, and you get better and better results. You see CPU time on my Mac over there. It's a bunch of seconds to train, so it's nothing really difficult. You can do more. This is a recent extension of this framework we did with Sampath Mulagaletti, who is a postdoc in our group. So here you want to do the following. You want to learn a model, say quasi-LPV model in particular, for control design. In particular, you know already that, say, when you use the model, you want to design a controller that must satisfy certain constraints. So for example, the output of the model should be between an upper lower bound, and the inputs you can generate must be between an upper lower bound. So you can identify the model, and different models will give you different properties of invariance under constraints. So our idea is the following. So let's try and characterize the conservativeness of each model we are identifying while we identify the model. So we came up with a regularization term on the model parameters, which is itself an optimization problem you need to solve, such that the smaller is this value for a given set of parameters, the less conservative is the model, meaning that you have a large set where the state can evolve while satisfying the constraints that you want to satisfy. So this is immediately a set you will use for control design, particularly for robust control design. And it turns out that this can be, even if it's an optimization problem, it can be auto-differentiated, so it fits within the overall JAX CZD framework. So we can solve learning problems, so learning dynamical models under this particular loss. Here you see a simple example of some data generated by a simple nonlinear oscillator with some damping, where we collected some 1,000 training data plus some other data we need to calibrate the set of output disturbances. So a simple model with 4 states, 6 scheduling parameters under this particular loss. So we end up with a model that has quite a large invariance set. So you know that if you start within this set, you will always find an input that keeps you within this set. And that means that the output of the system will stay within the bounds. So for example, here the controller we designed after the identification is able to track a reference while staying within this upper lower bound. So this makes the model that you have trained the least conservative for designing later a controller that must honor certain constraints on inputs and outputs. And let me show you another example, less trivial dynamics. So this is a benchmark, actually probably still the most challenging benchmark. If you're interested in benchmarks for nonlinear system identification, you want to try your algorithm, this is a rich repository. It's called nonlinearbenchmark.org. There are well-documented data sets taken from different application areas. So input-output sequences you can use to test your system identification algorithm. So in particular, I took this data set generated by an industrial robot. This is not that trivial, meaning that it has, first of all, has 6 inputs and 6 outputs. It's quite nonlinear, and it's also oversampled. So the difference between outputs at different time steps is very small, which creates numerical issues. And it's quite not very large, but still much larger than other data sets, about 40,000 training samples. Of course, the more training samples, the more complex is the optimization problem that you need to solve to train the parameters of the model. And actually, it's also not very informative, so the risk of overfit is quite there. So I tried fitting this model with 12 states, as is in the physics of the robot, with some neurons in the state updated output function. So you have about 1,500, 1,600 parameters. This is what you get. So these are R2 that you get, or the best in 30 runs that you get, depending on the L1 regularization you have on the coefficients. So this tau, the larger tau is, the more zeros you have in the model. So up to all the model coefficients are 0, so it's a constant model basically. Down with a small penalty, you have most of the coefficients not zero. Of course, as you increase tau, the quality of the model deteriorates, both on training data and also on test data. So there is some good compromise, like here, 0.008 is a good penalty, gives you a reasonably good model with quite about 30% of the coefficient which are zero, which is good because the model is more compact. And this, by the way, is what you get if you identify linear models. So the dynamics, of course, well-known, the dynamics of a robot are not really linear. If you try to fit a linear model, you get much lower R2 score compared to the nonlinear recurrent neural network model we have here. By the way, if you use more classical linear system identification tools, you get even worse models. See, these are, N4SID is kind of the most classical subspace identification method implemented in the MATLAB system identification toolbox, which due to numerical difficulties is not able to get the same quality of the model. And here is a comparison between this approach, where basically what I do is to first run Adam to warm start LBFGS. Adam is slow, but it's good to initialize. So it takes the right direction, starting from the initial guess to point you to the right place. So you can run Adam for some time, and then switch to LBFGS to refine, or if you want to complete the optimization. And I compare this approach in JAX-SID with OAL-QN, which is a kind of state-of-the-art method for training nonlinear models with L1 regularization. You get slightly worse results. You get some more sparsity, although it's more heavy computationally. If you run pure Adam, first of all, we take you more time, so you need about 6,000 iterations to reach similar quality. So you get, let's say, similar quality than OAL-QN on test data. But as you can see here, the percentage of zeros in the solution, it's actually almost zero. So there are all the coefficients but one are above the threshold. So that's why I prefer LBFGS plus Adam to warm start rather than just Adam. Now let me mention another method which still belongs to the class of quasi-Newton method, but that it's amenable for online learning. So let's say you have data that are coming online, so you're taking measurements and you want to adapt the model, so you want to refine the model. Or you can also use this for offline training, but you process the data sequentially. So extended Kalman filtering, which is used in nonlinear state estimation in many applications, can be used here for, not for estimating states, but rather to estimate the parameters of the model, actually both. So to estimate both the hidden states and the parameters of the model. The idea is quite simple, actually well known. So you can model the states, you can model the parameters theta of the model as if they were constant states that evolve over time based on some noise added at each time step. So if you assume that the model has a certain input noise, the parameters are perturbed by noise and the measurements are perturbed by noise, as in classical Kalman filtering, then you can design, decide covariance matrices for these noise terms and let the Kalman filter learn the models and the hidden states simultaneously by processing the data sequentially. You can do a one pass over the data, or if you want, if you work offline, you can do multiple passes on the data each time, updating the estimation of the initial state. And the covariances here that you choose these are a tuning knob, they play the role of the learning rate in training algorithms like Adam and friends. So the beauty of this approach is it gives, say, similar result for offline training, but it's is really good for online adaptation. So really to process new data without changing the entire model, just adding more information in the training data set to update the model coefficients. And you can generalize this. This is a recent work with our PhD student who just finished recently, Christopher Lowenstein, who applied moving horizon estimation as a generalization to AKF to also, let's say, to estimate the parameters and the state more effectively, and also to introduce constraints in the learning problem. What I did in this work I mentioned here is to extend this concept to arbitrary strongly convex smooth loss functions. So if you want, you can also train, for example, binary outputs, like you will have a classifier that has dependence on dynamics, for example, and also strongly convex smooth regularization terms. So you can generalize the extended Kalman filter iterations. Even L1 penalties, you can treat them as a limit case of a specific smooth regularization. And this will give you say, a change in the standard Kalman updates, measurement updates. Lambda is the penalty on the one norm, and P is the covariance matrix. And this update depends on the sign of the coefficients of the model. And here you see some results on a benchmark problem. So this is a data set from the system identification toolbox of MATLAB. It's a magnetorheological fluid damper system. Here are different results. The green one is extended Kalman filtering, so you get quite good model in terms of best fit rate on training, also on test data. Amsgrad is another first order method, which, as you can see here, performs more poorly. And in particular, you have to wait, but you have to wait quite a lot before the training quality gets better and better. Nails and NAIL are other quasi-Newton methods based on generalized Gauss-Newton method with line search or Levenberg marker steps that provide similar results. And yesterday I rerun LBFGS on the same data, and you get similar results. Actually, you get some slightly better results on test data. And this is same data set with slightly different architecture compared to pure Adam, and also compared to say nonlinear autoregressive models. These are taken from the demo in the system identification toolbox. You do considerably better both on training and especially on test data. And if you increase the L1 penalty, EKF still works up to a certain penalty where here there is a gray area where it starts not working well. This is not a method that is guaranteed to converge for every shape of the cost function and data. So convergence properties are local. So it works well up to, say, 10 to the minus 3, roughly. And you see how, again, how model quality changes with the penalty as expected. It gets smaller and smaller, still, say, acceptable, but at the same time, the percentage of zeros in the model keeps increasing, and maybe you want to take something around this area here. Okay, so again, I wanted to present this method as a tool for online learning when you want to refine the model. And indeed, we have applied these ideas for model adaptation, in particular to improve the quality of tracking in the presence of a model uncertainty due to the imperfection of the model. So the framework, well, first of all, let me explain why we have this issue with a model dynamics. What may happen, is actually what happens usually, is that if you have a simple model like a linear model and you want to track a reference, you will suffer some, say, offset in steady state. So you're not able to track the reference perfectly because there is a mismatch between what the model predicts and what the actual system does. So usually you need corrections to make this tracking error disappear. In particular, what is a standard practice in MPC, in linear MPC, is to add an output disturbance. So we assume that there is some unknown quantity, d of k, which has a constant dynamics, but we cannot measure, such that by taking measurements of the output and using a state observer to estimate not only the state but also the d quantity, then the combined output given by the prediction of the model plus this correction that we learn provides offset-free tracking. So motivated by these ideas, this is why this idea works in a nutshell. So in general, you have a nonlinear model, which is not perfect. You add a constant output disturbance. What happens is that the observer, say an extended Kalman filter, try to match the measurements. So the observer try to estimate the state and the d, the disturbance, such that it matches the measured output. At the same time, the controller try to make the predicted output match the desired reference. So as a result, the combination of these two action makes the output of the process, so the output that you're measuring, coincide with the reference asymptotically. So motivated by this idea, together with Pablo Krupa, who is a postdoc in our group, and Mario Zanon, who is a professor in our group, we came up with this idea. Say, okay, let's try and generalize this disturbance model, not just to be a constant, but to be a small nonlinear model, which has its own coefficients, theta, that enters the output, may enter also the state equation, and may also depends on the state and the inputs. Why a simple model? You don't want to remodel the entire system. Say you have already identified the system, or you have already obtained a physical model of a system that you don't want to change too much, because you want to rely on new data, but also you don't want to rely too much on new data. You may drift the model away so that when you come and jump to another set point, the model doesn't apply anymore, so it's completely drifted. So you want to keep the baseline model, just adapt to improve the model in the operating regime you are. So this would be a simple disturbance model that you want to train online. So what you do is to use the extended Kalman filter that you typically use to estimate the states. You extend the state with the parameters of the disturbance model and estimate both the states and the parameters of the disturbance model, as I was showing before. And it turns out that this is it's quite a good idea. So here is an example of a nonlinear chemical process. You want to control the concentration of a certain reactant in a tank by changing the temperature of this jacket here and measuring the temperature and the concentration of the inflow. Excuse me. The model is quite nonlinear, although it's simple, but it's quite nonlinear. So here is what you get. So if you have, say you want to track a certain reference, this is the reference. If you have a perfect model, then after the first transient, the tracking will be perfect, no mismatch. If you use a linear model, like in the middle here, you have good tracking because the constant disturbance model can catch up with the changes in the model. I see there is some transient here where the tracking, you better see here, where the tracking error is not very good. And here's what you get if you have a simple neural network model that try to identify a simple disturbance model. So not perfect because you're not capturing the exact dynamics of the system, but it does quite a good job in understanding the changes that the dynamical model is having during the operation. So during this change of set point, this is actually quite a wide change of value in concentration in the tank. So this is a good idea that can be applied in situation where you want to update the model due either to changing changing set point. It could be to changing environmental conditions like outside temperature, or even change part-to-part variations of, say, in a mass production, the systems are not exactly the same. They're nominally the same, so the baseline model is good, but they're not exactly the same. You want to refine the model at runtime while you go. Now let me show you another say set of learning ideas that we have been used to actually try to learn the performance index that we need to specify to implement the MPC controller. So I mentioned MPC has two parts, the model and the cost function you want to minimize. Now let's focus on the cost function. So we recently looked into this problem. Say, okay, let's say we have a data set of certain variables, x, and certain parameters. So we have a parametric function that we want to learn. And we want this function to be convex. So let's say the data set is generated by this nonlinear function. These are the level sets, so it's quite non-convex. You want to find the best possible convex function that fits this data, so that resembles the function as much as possible, but it's convex. Why do you want the function to be convex? Because later on you want to minimize this function with respect to x for each given theta. Okay, so for example, theta could be the set point, and x could be the sequence of input variables, and this f would be the performance index. If the performance index is convex, and you have a linear model, and actually you can ignore the model, just minimize the convex function subject to, say, you have convex constraints on the inputs, then your problem to solve online will be a convex optimization problem, which is much easier to solve compared to general non-linear, non-convex optimization problem. So in the simplest case, for example, you could parameterize the function as a quadratic function where the Hessian is positive semi-definite, and for example, this could be a neural network of the parameter vector theta, and this can also be other neural networks. So we tried with, there are many actually different architectures that have been studied, well, not many, some architectures have been studied for what are called the input convex neural networks. So neural networks that are convex with respect to the input. So they don't need to be convex with respect to the parameter, which become fixed at each optimization you do later, but they are convex with respect to the input x. So recently with the group in Stanford with Stephen Boyd and Max Schaller, who is a PhD student with Stephen, we tried to generalize this class of functions, what we call PCF, so parametric convex function. So think about the function as the following. So x is the input, theta is the parameter. So this is a standard fit for a neural network with some restrictions. So the weights of these networks are generated by another neural network psi, which consumes the parameter vector theta. So this could be an arbitrarily complex network that generates the parameters of the neural network that estimates, that estimates the output y as a function of x given theta. And there are some restrictions on these weights and on the activation function. In particular, the activation function must be non-decreasing and convex. So for example, ReLU is non-decreasing convex, soft plus is non-decreasing convex. So there are many activation functions that are used which are already non-decreasing and convex. And also the weights W that map previous layers into the next layers must be element-wise non-negative. So under this restriction, you can show that the function you get out, so y as a function of x, is convex. It's convex no matter what is in here, as long as these two requirements are satisfied. Now, this Psi network, we model this as another feed-forward neural network. And how to impose the non-negativity of the weights, we simply, at the end, so at the last layer, we simply either clip the value of the last layer to 0 by a ReLU, or take the square of the linear output function so that we get non-negative weights, simply as this. So we have implemented this in a package called LPCF, which relies on JAX ID for the training, for solving the training problem under L1 penalties that you can specify. It's quite, I would say it's quite flexible and customizable. And as an output, so you give as an input the data set, so the function values that you measure and the corresponding inputs and parameters that produce those values. And as a result, you get out a function, either in JAX, that you can use later for fast evaluation or for autodiff, and also CVX-Pi expression. So CVX-Pi, it's a very good environment for formulating and solving convex optimization problem developed at Stanford. For many years now, it's quite popular and quite powerful. So what you get out is a CVX-Pi expression. So say the workflow would be like this. So you get your data, so the function values, x, input, theta parameters. You fit this data into parametric convex function. And then if you want to use CVX-Pi to solve an optimization problem, so you specify there is a variable x, a parameter theta, y is the function you have fit operating over x and theta, and then you can use this value y in your problem. For example, you want to minimize y plus something else, or use y as a convex constraint or whatever. Or you can export to JAX. So this f would be the JAX implementation of the function that you have fit over the data. So there are many different features here you can use already available in the package. First, you can impose a convex quadratic term so that the function is the sum of a quadratic term plus an input convex neural network. You can require that f is monotonic. For example, you're fitting, say you're fitting a utility function you want to have strictly increasing. You can ask in the options to have the function to be monotonically increasing, or minus the function to be monotonically decreasing, or to be non-negative, depending on what you are, the purpose you are fitting f for. Or if you know that the f you're learning has a minimum somewhere, so for example, you know the minimum must be always 0, or it's a function of theta, then you can impose, or at least ask that the function you're fitting has a minimum with respect to x at this function g of theta for every theta. Or you can solve what we call the convex classification problem. So I have binary data, which may not belong to a convex set, like in this picture here. Say green is +1, orange is -1. These do not form a convex set. So you want to find the best convex approximation of this set. So the best convex function such that f smaller equal than 0 identifies a convex set, since f is a convex function, which capture this binary data point as at best. And here is an example of how you can use this parametric convex function approximation tool for control design, in particular to simplify a given design. So let's say your dynamics are expressed by a nonlinear model in what is called input-affine form. This actually sounds not too general, but it's actually quite general. So the input appears here multiplying a function of the state, and then you have another term for the state update. And you have some performance index. H is some loss that you want to optimize over, say, an infinite horizon between time 0 and the future, which later on will become current time and the infinite horizon in the future. Now, this is a complex problem because the model, as you iterate over time, generates non-convex functions of the input sequence. And the H term here could be also non-convex. So this could be quite a non-convex problem. Now, what you can do, you can split the sum as the first term plus the, say, what is called the cost to go, and then fit the cost to go. So by Bellman principle, this means to fit the cost from 0 to infinity as a function of the initial state for each given parameter theta, so that later on, by applying approximate dynamic programming, instead of minimizing the cost over the infinite horizon or over a long horizon, you can minimize the current cost with respect to the current input u plus the cost to go. And if f is convex, and this is a given constant term, once xt is given, theta is given, this is given, u appears linearly. So this term here is convex with respect to the input u. And therefore, if the loss you're using here is convex, this is a convex optimization problem. It's actually a simple convex optimization problem with respect to the current input u. And here's an example. So it's an academic example. You want to swing up an inverted pendulum. Its academic is actually quite convex. You have two states, position, angular position, and speed. Instead of solving to generate the data set, instead of solving an infinite horizon problem, we solve a problem over 150 steps, which is more than enough. We collect optimal data. So this is generated offline by solving a nonlinear optimal control problem. And then with this data point, we fit a function, and then use CVXPy to solve this simple problem here at runtime. And it turns out that you get very close. So this is the u star 0 is the output you will get if you solve the full nonlinear optimal control problem over the long horizon. And this is the simple outcome of the convex optimization problem. They are quite close to each other. And of course, it's not perfect because you're modeling with a convex function something which is actually quite non-convex. But it's close enough. And indeed, in the closed loop, the trajectories look quite similar with really a small fraction of the computational load. And finally, let me show you another, even more recent application of this concept of learning the function to minimize, in this case from preferences. So we don't have a function we want to minimize. Why? Because sometimes, so in real practice, the MPC cost function is not really given. Usually it's a design parameter. So you put some weights and then change these weights so that the closed loop performance you observe is what you expect. Or sometimes, if you have really clearly like a KPI you want to optimize, you can use that if it's not too complicated to minimize as a performance index in the MPC problem. But sometimes you don't have this performance index. Or either you don't have, or you have too many. So you have multiple KPIs. So multiple performance indexes you would like to minimize. Which one do you choose? So you can get a combination of those, but which combination of those objectives? Not clear. So you may have to try different weights to different cost terms until you're satisfied. And sometimes you don't even you're not even able to quantify exactly these performance indices. Sometimes it's, say, it's in the head of the calibrator, say, this looks good, this doesn't look that good. Why? Maybe there are some rough ideas, but sometimes it's also experience, and several factors that are not easily quantifiable in a mathematical form. So what you can do in this case to train, so to decide the MPC cost function and other MPC degrees of freedom in the design is to use preference-based optimization. So the idea is the following. So say you parameterize the control policy. In the case of MPC, this could be the weights. And then rather than optimizing a given performance index that you don't have to decide which is the best combination of control policy parameters, you compare closed-loop trajectories and have either an algorithm or a human calibrator to tell you which one is better, and do this iteratively. So this is an active preference-based learning of the best control policy parameters, or a preference-based optimization of the preference based on preference of the control policy parameters. This can be solved by Bayesian preferential Bayesian optimization. We developed another idea to solve this preference-based optimization together with Daniel Piga at ITSIA, SUPSI in Lugano, using radial basis functions. So the outcome would be a set of parameters. And actually we have programmed these into a package called GLIS, which also implement this preference-based optimization. Now, what we want to do, recently looking at in Luca, is to not even parameterize the control policy, but rather just compare trajectories. I show you two trajectories, input and state trajectories. You tell me which one you like on a set of comparisons. And based on this comparison, I give you the MPC cost function to minimize. And the idea is the following. So let's consider generic set of pair of input and state trajectories. So you run your system for, say, 30 steps, so some finite amount of time. You collect the input and state trajectories, and you collect comparisons. So if I give you two different trajectories, say Ti, Tj, you, human or another algorithm, tells me if the first trajectory is preferable to the second trajectory or vice versa. So it's a 0-1 information on which of the trajectory looks best. You can extend this to 1, 0, -1 in case you want to model also no preference. But let's say this is a basic framework. Actually, it's flexible enough. Now, if you can collect, say, a set of trajectories and a set of comparison among those trajectories, you have binary measurements. So as a function of a pair Ti, Tj, you have the corresponding preference. And then you can make the following assumption. So let's assume that there exists a latent function, which I don't know, so completely unknown function sigma, which is a function of the trajectory, which I don't know, but I assume it exists and is the one that generates the preferences. In particular, you get a preference 1 if sigma applied on Ti is smaller equal than sigma applied on Tj, or vice versa, 0. So if you parameterize sigma as a parametric convex function and simply have a binary classifier defined on top of this parametric convex function, you can fit this preference information. So you can find the parameters of the PCF that best explain the preference measurements that you have collected through this assumption of being generated by a latent function. And then, as a result, say if you have a good fit, then this sigma function that you estimate, which I call sigma hat, the estimation of this function is something you can use to to optimize. So if you can train this function, then online, given the model of the process, you can directly minimize this function. This is a function of the trajectory. So it's a function of the predicted states and of the inputs that you're optimizing over the prediction horizon. And in particular, if f is a convex function, this would be a convex problem. Okay, and also if the set of feasible inputs at state is convex, this would be a convex optimization problem, so an easy to solve problem. And we have tried this on a simple example to see this makes sense. So this is a simple 3-mass oscillating systems. The real latent function that we assume not to know is actually a quadratic function. So we want to see if we can retrieve this function just from preference. And as you can see here, so the blue one, which I'm zooming in here, is the true function. So if you really minimize this function, you will have this blue line, which is, say, the best behavior. If you collect more and more preferences, you get closer and closer to the real behavior. So actually, you are understanding what's behind the mechanism that generated the preferences just by looking at input state trajectories. This still work in progress, but that's the main idea. All right, good time to draw some conclusions. So my message here was trying to give you some examples of how classical ideas from machine learning, more or less classical ideas from machine learning, can be very useful to solve control problems, in particular to get good control-oriented models from data, and also to design control laws directly from data that you collect. And of course, machine learning, I like to always say this, that machine learning cannot replace control engineering. So if you just blindly apply, say, deep learning, take PyTorch, standard classical setup, try to fit a model, probably that will not be a good model for what you want to make. You really have to tailor the learning tools to what you want to do, and always have the, say, control engineering insight of what you are doing and what are the requirements for the model and for the rest of the ingredients in the control load you're designing, so that you always want to keep in mind. Of course, there are alternative methods, and I also like to mention this post by Jan LeCun, mentioning about the relation. So it's actually very sharp on this. So indeed, I do favor MPC over reinforcement learning. So reinforcement learning is very popular, actually quite powerful and effective in many applications. So you could say, okay, let's get rid of all these model-based control design, online optimization, just train using reinforcement learning and controller. Well, this could be quite disappointing. First of all, you may need lots of data. So it's well known reinforcement learning to be less sample efficient than model-based control design. The reason that you're trying to learn the model and the controller indirectly, the model and the controller at the same time, which is difficult. So if you can afford doing a model based approach, like learning a model and then using the model to design the controller, this is a lot more effective. An example that I gave here is MPC, which is model-based. And in fact, what Jan mentioned is I do favor MPC over reinforcement learning. And reinforcement learning requires ridiculously larger numbers of trials to learn a new task. In contrast, MPC is zero shot. If you have a good model, good word model, and a good task objective, then you can solve new task, and then it continues the same. So the message is that, and this indeed is true in practice, once you have a good model and a good objective, you have most of the work done. You have to fine-tune, but you have most of the work done. And this is very effective to generalize. So since you have the model, the physical model in particular, even if it's data-driven, if it's not physics-based, it's data-driven, can be quite effective in capturing what the system does also in areas that you have not explored carefully. So it can, I'll not say extrapolate that much, but it can interpolate quite well. And therefore, the control law, which exploits directly that model, can be, as a consequence, quite effective in controlling the system optimally and within the constraints. And there are some open problems we're currently looking at are active learning methods to help collecting good quality training data to learn the dynamical models. The work that my PhD student Kuishi is doing at IMT. And also we're looking at different nonsmooth nonlinear optimization method and just LBFGS to handle learning problem with constraints that sometimes you need to include in the learning process to get models that have certain intrinsic control theoretical properties that you need to design the controller. And all these activities are under the ERC Advanced Grant Compact funded by the Commission. Okay, that concludes my presentation. And thanks for your attention. I'll be happy to answer questions if you have.
Thank you very much. Very deep, indeed. So open the floor to questions, especially to those who were able to fully follow all the maths and the algorithms that were inside. Whoops, sorry for that. For whoever wants to ask a question, there are microphones available. There. Okay, so raise your hand again, please. Next in line.
So, first of all, thanks for this presentation. I have a question, a curiosity. We saw that there are different algorithms to minimize the function, the cost function. I think it's important in the choosing of this type of algorithm, the horizon step that you have defined in the application, because if your forecast is very long, the approximation of the error it's bigger than. Is it correct, this type of approach?
So you're referring not to the optimization algorithm for training the model, but actually using the model for solving the MPC optimization, so yes, to minimize performance over prediction time. Yeah, the prediction time, of course, it's a relevant part of the design. So you have to forecast long enough not to be too myopic. If you're too shy, say, short-sighted, then your control may not behave well. Like when you drive, if you don't look ahead too much, you just look ahead a few meters, you have a risk to bump the car preceding you. So you have to have a long enough horizon. As you say correctly, not too long, because then the model, as the prediction gets longer and longer, of course, deteriorates the quality of the prediction. In practice, this is not a big deal because of the receding horizon. So you forecast, even if the forecast is wrong, and it's more wrong and wrong as you proceed in the future, you are correcting your action at the next time step. Okay, like again, when you drive, even if you don't wear your glasses, so you don't see too far in the distance, but you're doing maneuvers which are good enough, you can catch up and correct your actions later.
Thanks.
She had a question.
Thanks a lot for the talk. It was very interesting. I have a question about, I think, slide 10, so very early on, where you have this function that you want to minimize, and to remove the dependence on the latent variables, you use the function f within the function that you want to minimize. I was wondering if it's possible to marginalize out instead. So to integrate out the latent variables instead of substituting the f, if it does make sense at all.
So what you're exactly proposing? So to keep the latent variables as variables, or
so instead of plugging in the f, integrating out the x, and so define.
So that's what you're doing when you substitute. You are integrating the model by substitution. Indeed, that's what you're doing. I mean, the substitution is the discrete time integration of the model with respect to time, no?
Yeah, I have to think about it for a second, but yeah, thank you.
Yeah, no, that's exactly what you do. You substitute. So it's like you're simulating while you optimize, like you're simulating the model, given the initial state, which is a variable to optimize. You are simulating the model over time to produce all the outputs that you compare with the measured outputs. And then the simulation only depends on the initial state and the inputs that perturb at each step the evolution of the state, which remain the only variables to optimize.
So you are integrating with respect to time.
Time. Yes.
Sorry, what I had in mind was integrating out the x.
Oh, the x. Yeah. That's I'm not sure how you would apply in this context.
Pretty much my question.
Yeah, maybe with some. Are you thinking about like this, like PDEs, or I mean, infinite dimensional state models?
I didn't have any particular point in mind.
Yeah. Okay. No, I don't know. Maybe it's a good idea. Yeah, I don't know.
Thank you.
Hi. First of all, thank you very much for the nice presentation. I have just a curiosity about the complexity of the neural network that you can use inside the model. Besides the, of course, computational requirements that you need if you use bigger or more complex model, is there any trade-off, let's say, between the convergence, maybe ratio, or maybe on the quality of the result that we can obtain using very complex network? Maybe
this is an excellent question. Thanks for asking this. Because one reason I didn't mention why simpler models are sometimes more useful than more complex models is exactly what you say. So these are non-convex optimization problems. And actually, the deeper the neural network you're using, they say the more non-convex the problem becomes. So in practice, what you observe is that you have, say you have 2 layers. You can get a decent model. You add another layer, and you get a much worse model. So you cannot find an initial guess that gives you even the same quality of the model. So there is really a trade-off, exactly for what you said, between the complexity of the model and the ability to solve the training problem due to the non-convexity of the overall training problem.
Okay, so overall, if I get it correctly, basically adding very complex model decrease the quality of the solution because it's very difficult to optimize and to find.
Can decrease, not always.
Can decrease because
hopefully
it's very difficult
does
to
not,
find
but
like
yes.
an optimum basically, or at least a good one, let's say.
Yeah,
okay.
cool. There is a lot of studies on this. For example, if the model gets more and more complex, then actually start easier to solve the optimization process. Kind of have a convexification in higher and higher dimensional spaces. So I'm not an expert in these things, but so there are some studies which show that the training probably becomes more and more difficult, and then it actually starts getting less difficult as you increase the model even further. The problem is that if you have very complicated models, then there is no use for those later.
Okay. Regardless of the algorithm that we decide to use. Because I can imagine
I would say
maybe ADAM maybe can help to avoid some local minimum and not LBFGF that maybe start to drop.
That's why actually I'm using ADAM to warm start LBFGS. But anyway, for example, in Justice ID, there is a command called parallel fit. Usually you try, say, 10 or as many cores you have in parallel, and say try 100 different initial guesses. For simple network, it doesn't make much difference. But if you start increasing the complexity, of course, you start seeing different. You get a good model at seed 89 out of say 216.
Okay, thank you very much. Thank you.
Any other question? Nope. So thank you very much, Professor Bemporad. Thank you again on behalf of AI4I and the Fondazione Compagnia di San Paolo. We can close here. I would just like to remind you our next event, which happens on next Monday, 22nd of September. We will host here Professor Zecchina, who is Vodafone Chair of AI at the Bocconi University. As you can understand, Bocconi is doing more things than they used to do in the past. And he will talk to us about dynamical learning in deep neural networks. So again, pretty technical and interesting frontier topic. The next one will happen in the morning, so reception will start at 10 o'clock, probably start like 10:30, something like that. Thank you very much. See you soon.
Thank you.
Bye-bye.